Okay. All right, gases. I love gases. So I'm glad we have 3 days to kind of take a look at gases. A lot of stuff makes sense with gases. Of course, gases we've talked about, it's just a phase of matter, right? Matter can be a solid, liquid, or gas. And you keep that. So gases are great. So if I was gonna write what a gas looks like, you know, if you're a visual person, you know, matter can be a solid, matter can be a liquid, matter can be a gas. And over here, it's really connected. So we said high bonding and low KE. What's KE stand for?
Kinetic energy.
Mm-hmm. Yep. And as a liquid, it has some bonding. And I'll put moderate, MOD, moderate KE. And what about gases?
They have low bonding
Yep.
and a lot of kinetic energy.
Yeah, exactly. Low bonding. And they have lots of KE. They are like banging around. Gases are so wonderful. Okay. So gases have a lot of like general properties. One of them is they're compressible. If you've ever gotten compressed air, basically it's air that's squeezed into a bottle. Okay. So gases are compressible. So I've got some figures to kind of show these different properties of gases. So this, when you're looking at it, is like a piston. I call it a piston. But this thing right here, okay, has like a plunger that can go up and down. Mm-hmm.
So you know when you have a computer, you have a little pressurized air that
Mm-hmm.
you use when you have a keyboard? Why
Yeah.
is that cold?
Why does that get cold? Well, if you shake it, can you almost hear some sloshing of liquid in there?
Yeah.
Okay, so when something goes from a liquid to a gas, it requires energy. It's very what we call endothermic. So as that goes from a liquid to a gas, it is like robbing energy from the environment. So that's why it gets cold.
That's why you're not supposed to shake it or turn it upside down.
Really? Okay.
Yeah, it says it on there. Have you ever done it? When I was little, I did it, and like the whole outside of it froze, like there was frost.
Oh, goodness.
Yeah.
So, like, yeah.
It was crazy.
Related to that, oh my gosh, I saw on Facebook where you can make it's like a magic slushie, and you know, like when you make ice cream, what do you do to them to the ice cubes?
You just
What do you put? Yeah, you put salt exactly
Yeah.
in the ice cubes, and what that does is it lowers the freezing point temperature, okay, of water. Okay, so what that does is actually you can get ice at a temperature below 0. It's like pushing, well, below 32. It's like pushing, I don't know, 0 Fahrenheit. It's cold. So anyway, yeah, magic slushie is you take 2 Ziploc bags. One Ziploc bag you put ice and salt. In the other Ziploc bag you put your yummy juice. That's what I did. And then all you got to do is massage the juice for 5 minutes.
I
And
made ice cream like that.
turns
in
into a
high school.
slushie.
We
I
did that in
love it.
I think it was 3rd grade or something outside.
Well, I'm just now discovering. I love it. I think everybody should eat magic slushies. So,
At least it didn't bust. I'd be scared it would bust.
yeah. So gases are compressible. Okay. So what do you think? Over here's a liquid, you know, and these little liquid particles, can you compress them? Not so much. It'd be harder. Let's see if this will go back to me. Back to this one. So another general characteristic about gases is they entirely fill their container. Gases are wonderful. And it kind of makes sense if you think about it. They have so much kinetic energy. Why not fill the container? So here is a picture of, have you ever seen that? Now this doesn't have to do with gas, but the advertisement with the wind, where he takes some wind and he puts it in a bottle, and I think it's wind. Anyway, these are gas particles, cute little gas particles in the jar. What else about gases? gases have their densities. Remember we said density is kind of how fluffy or how dense something is. So if density, symbol for density, of course, is that Greek letter rho, that's density. What we do is we take a certain object and we measure its mass and we divide its mass by its volume. And that gets our density. And see, to me, what I would say is the fact that we said gases are compressible, i.e. changing volume, that's my thing. Okay, if you can change the volume, okay, then you're changing the density. Like on the figure we looked at just a minute ago, if you can squish it down, you made it more dense. Okay, what's the next one? Gases are relatively sparse. They have low densities. And you can kind of see that in these figures. Like if you compare this volume to, excuse me, this volume, okay, this is a lot more dense and this is less dense. And your textbook has a figure to kind of show you what that is. So the way this works is we have cans of soda. If we were to take one can of soda and go ahead and take it from its liquid state to go ahead and vaporize it, now it's just sugar water, right? So we're going to end up with mostly water particles. We go ahead and vaporize it. What that volume would be equal to, that new volume as a gas would be equal to 1,700 cans of soda. Now, I guess I would argue that it depends on, this must be at standard temperature and pressure, but it depends on, once you gasify it, you know, what your temperature and pressure of your soda is. So that's that. What else? Gases want to mix to form, we talked about two types of mixtures, heterogeneous and homogeneous. Gases want to be a homogeneous mixture. They want to homogenize, and it makes sense, okay? So, and kind of the reason they want to homogenize relatively quickly is, by golly, they got all this kinetic energy, they're going to mix it up. So we kind of have a figure from your textbook that looks like this, where the different colors are the different colored gases. And so the first one is an empty cylinder. We go ahead and put CO2 is blue, and then we go ahead and add argon to it. And given time, it's going to form a homogeneous mixture. It's not going to layer up. Okay. Oops. The next one, maybe almost, yeah, this is the last one. Now, an important property of gases is the pressure that the gas is exerting. And to me, you can only gauge pressure if you realize that basically it's banging against the walls of its container. All gases do that. I say that, and yet, like in this room, there's nitrogen and oxygen. We're quite familiar with it, or happy with it. But it's not contained per se, but is definitely exerting a pressure. If we were to go to a different planet that had different pressure, okay, you would know it. Okay.
So, I was watching, I think it was like CSI or something, where this guy he was buried alive in because they were trying to kill him. Like, they were trying to murder this
CSI
guy.
people were? Or somebody else was?
No, I mean,
know.
I don't remember. But it was like, he was going to run out of air because the gas was going to turn to carbon. So I guess if you sealed this room off completely, eventually it would run out.
Yeah.
It would take a long time.
Or it would
Yeah, depending upon, like, if you're in a small area, you'd run out fast, but a bigger area. But yeah, if you sealed it off, we would convert all of the usable oxygen, which we need, into carbon dioxide, which is deadly.
Unless you have like a couple of plants in there.
What's that?
You need a lot.
You need some plants in there.
Yeah, need some plants in there. That's why, like, people in coal mines, yeah, like if they have an issue, they don't have fresh air coming down there. Yeah. Very good. Oops, we already did these. Did that one. There's one we didn't do. This is the one we didn't do. So this is trying to kind of show you that all gases exert a pressure. And I guess to be better, I shouldn't say that all gases are confined and they exert a pressure on their container, but all gases exert a pressure on wherever they are. And so, all right.
What do you call the pressure? Jeez. Okay, so like when you break your arm and the pressure changes in the atmosphere, you can feel it, like in your bones. I don't know. You
Yeah.
have it?
Yeah, like in arthritis too, also people with bone issues can
Yeah.
feel the pressure changes.
Yeah, I totally can.
My mom talks
Yeah.
about that all the time. She broke her ankle a long time ago, and I guess whenever it starts to rain. Also, if you have sinus issues.
Yeah, oh yeah, the pressures with your sinuses, oh, yeah. Yep, and the atmosphere, and we talk about this in weather, is, you know, the atmosphere is always kind of changing the pressure. In fact, we're gonna talk about that here in a minute, okay, the pressure of the atmosphere.
Like when you go outside and you have a balloon, and the balloon kind of flattens a little bit when you go outside, especially if it's cold.
Yeah, yeah, exactly. That's one of the
That
cool things
sucks.
about gases. Yeah, but if you heat it up again, what's it do? Reinflates.
No, my niece's birthday is in February, and I got a whole bunch of balloons for her, and I went outside, and they all hit the ground. I was like, oh my god.
Because it was cold, right?
Yeah.
Yeah. I want my money back.
I know. I was like, are you kidding me? They were like, no, just put it back in your car. I was like, okay.
Oh. So when it comes to gases, and we'll be talking on Wednesday about some problems dealing with gases. Okay? But when it comes time for gas, a lot of times I will draw a box and I'll make my little gas particles in there, spread them far apart. Sometimes I'll even make a little arrow to show that they're banging against the walls of the container. And in order to work problems with gases, we need to know the pressure of the gas, and we'll talk more about pressure, what pressure is. We need to know the volume that's containing the gas. We need to know the temperature, because you guys just told me that temperature is a player in how gases behave. And then we need to know the number of moles, and the variable we use for the number of moles is N. Okay, so that's just kind of new. So anytime you see N in chemistry, that's moles. All right. So what do we mean by pressure? Well, pressure of anything, including gases, is always the force that you're exerting over the area that you're exerting. So it's a division problem. So it's force divided by area will give you pressure. And it kind of makes sense. So for instance, if I take my whole fist and I'm pushing against this much of my hand with this amount of force, okay, that's actually going to be less pressure per area than if I do the same amount of force and I just have on a finger. Okay, that's more pressure, okay, because it's a smaller area. Same force. So anyway, so pressure is force divided by area over which the force is working. And so what is force? Well, there's different ways to talk about force. One way is Newton's force is equal to mass times acceleration.
Do we need to know these?
No, no, I'm just kind of putting it in context. Units of force are the newtons. Okay, that's a unit of force. So if pressure is force divided by area, then we have to take newtons and do something with it in order to get pressure. So here we go. So we aren't going to use units of pascals as pressure, okay, but they are good units. Pascals are a great unit for pressure. Okay, 1 Pascal is 1 Newton of force per 1 meter squared. Okay, so we're going to switch gears and we aren't going to use pascals, but it is a unit of pressure. So the units of pressure we are going to use, if you want to take a circle these top 2, you can, because that's the most important, I think, in chemistry problems. There's one more, which is a torr, but, and we were talking about, you know, how bones and we react to what the weather is doing, what the pressure of the weather is doing. The pressure of the weather is generally 1 atmosphere pressure or 760 millimeters of mercury. And you're like, what millimeters of mercury? How do you get pressure out of that? And I'll show you a mercury barometer here in a minute. So another unit of pressure that we use in chemistry, we aren't going to use it this semester, but is a torr, okay? And a torr is exactly equal to 1 millimeter of Hg stands for mercury. So 1 millimeter of Hg, 1 millimeter of mercury is equal to 1 torr. The top equivalency statement is an exact relationship. So I think I'm going to go ahead and, for your homework, I'm going to assign something that's due Wednesday, and you're basically, it's warm in here, isn't it? You're basically going to kind of convert within these different systems. Okay, oops. So this last one right here, 14.7 psi. Of course, that's like if you go to put air in your tire, you'll probably need to put like 65 or something psi. That stands for pounds per square inch. So pounds are force per square inch, that's area. So that's kind of fun. And these all coincide, let's see, how do I say this? These are all typical atmospheric pressures. So the pressures of the atmosphere, okay, here on Earth, at the Earth's surface anyway, these are typical. But a little bit of change in them can kind of really make things interesting weather-wise. All right, that's better. So here's a figure from your textbook relating atmospheres, millimeters of mercury. Oops. Okay. You guys don't have anything else to add there, do you? Okay, so now I kind of want to take a trip through, oh, that makes sense sort of thing. So for instance, let's see, pressure. So what if you, like you can see between these two jars, the jar B down here, the second jar, just has a bunch of more gas particles in it. Doesn't it make sense that the pressure increases? Okay. So this basically, if you want to kind of put it this way, an up arrow means increase. As you increase N, what's N? Moles, gas, yep. As you increase N, that will increase pressure. Makes sense. It's like blowing up a balloon or something like that. You're increasing N, increasing the number of moles. Well, this is actually going to show you when it says 760 mmHg, millimeters of mercury. Of course, you know millimeters is a length or a distance. Okay, and this is actually where the 760 millimeters of mercury comes from. It's from a liquid mercury barometer. So the way this works is we have, and liquid mercury is not a good thing to necessarily be around. Okay, so but this is HGL, mercury, liquid mercury, and this is open down here, open down at the bottom, and it's closed up there. Okay, and basically what they do is they take the tube that's open at one end and closed at the other, and they create a vacuum, so there's no particles. And then, I know they don't do this, but they kind of put their finger on one end, and they kind of just dip it into the pan of liquid mercury. And then it kind of settles. So depending now upon basically what's happening with this pan of liquid mercury down here, as the pressure, this right here, this blue arrow, that's the pressure of your atmosphere. That's basically the pressure of your atmosphere, or gas, but in the case if it's in a room, it's the pressure of your gases in your atmosphere. So as that increases, as this increases, then it will make the liquid mercury go up more. So 760 millimeters of mercury is actually a length of how far up that mercury went up in the column. Okay, so here's another one. Okay, we did a minute ago, we said as you increase moles, it increases pressure just a minute ago. Well, here's one for you, and actually this goes back to your niece's balloons. Okay, as you decrease temperature, what happened to pressure? Yes, decreased temperature, decreased pressure, exactly. And that's the relationship that gases have between temperature and pressure. Now, we're used to using equal signs a lot. I'm going to introduce a new mathematical symbol. It's not equals, actually it's a proportionality symbol. It looks like an infinity with a bite taken out of it. Okay, that's proportionality, proportional symbol. So when we said as the temperature goes down, the pressure goes down, when they're lock and step, we say that they're proportional. So we say that the changes in I like to think of as temperature exerting an effect on pressure. So as we say the temperature and pressure are directly proportional. As you take your balloons from a cold environment to warm environment, what happens? They warm up and your pressure goes up. Okay, makes sense. All right. So I have a few little animations. Oh, what about pressure and number of moles? We already did that one, didn't we? Okay, we said if you increase number of moles, you increase pressure. So those are also directly proportional. So we just say P is directly proportional. That's how you read that to N. That's awesome. We'll have to wait for this video. And then the last one I want to look at, I think it's the last one, is pressure and volume. So here's one for you. And I don't start with pressure, I start with volume. So what happens if you take a balloon that's all floppy, has kind of maybe low pressure, has a certain volume though, and you take the volume of that balloon and you reduce the volume of the balloon, what happens to the pressure? It goes up, exactly. Reduce the volume, pressure goes up. Okay, what happens if you take something that's really dense and you let it go ahead and let the volume go out? As volume increases, pressure goes down. So finally now we have something that we call this relationship actually inversely proportional, not directly proportional. So we can use the proportionality symbol if we do this. If we say volume is proportional, directly proportional to 1 over pressure, basically the flip over pressure, the inverse of pressure, that works. Okay, that's showing an inversely proportional situation. Okay, so as one goes up, the other goes down. Okay. So this is showing you, like what you just told me with regard to pressure and volume. Along the x-axis is volume, along the y-axis is volume, along the x-axis is pressure. So as we decrease the volume, the pressure increases. So you're right. And hopefully you see this one on Wednesday. So we have this assignment, and I mentioned that, and some of you are really ahead on your extra credit points. So feel free, but the first one is going to be extra credit because you can see the answers in the back of the book. Yeah. Well, no, the first one is real credit and the other one's extra credit. Okay, sorry. So this is real and this is extra credit, 10 points extra credit. And they look kind of like this, so we'll take a look at them. They were the ones I said going back and forth between the different pressure units. There it is. Okay. So just to recap, this is worth real credit, and this is worth extra credit. All right. So then I went ahead and brought in a table from your textbook. So look at these as they are all equal. So these are all equal. So you could come up with the quality statements. Look at them as exactly equal. So for instance, let's set the first one up. So if we're looking at A, basically you're supposed to go from millimeters of mercury to ATMs, atmospheres. Okay, so the first term is going to be 1277 mmHg over 1, and then your next term you're actually going to get from the table. Or it's not a term. From the table, we can see that these are equal. 1 atmosphere is exactly equal to 760 millimeters of mercury. Okay, so if we want millimeters to mercury, to cancel, excuse me, we'll put 760 millimeters mercury down the bottom, and we'll put 1 atmosphere on the top. Does that make sense? Okay. So you can do those for all of those. So let's take a look at the last few slides. There's no more assignment slides. And then next, on Wednesday, we'll talk more about gas problems. But again, if you have a gas, in order to kind of fully describe the gas, you don't have to tell its identity. I think that is so cool. All you got to do is tell what pressure it's exerting, the temperature it's banging around at, and what volume it's being contained by, and the number of moles that are in that container. I just think that is so cool. So a few things. We do need to touch base about the temperature term, the T term in gas problems. It actually needs to be in units of Kelvin. Okay, so I think we talked about temperature way back in Unit 1 in here. But we're most likely to use Fahrenheit scale here, us. Celsius scale is better because it's metric. Even better than Celsius is kind of the Kelvin scale. Okay, so, and one of the things you're going to want to be able to do, I don't know, you might want to even put it on your note card, and we'll look at problems where you need to do these conversions on Wednesday. But if, for instance, if you're given the Celsius temperature and you need the Kelvin temperature, here's how you do it. You add 273.15 units. And that's because the unit on the Celsius scale is equal to the unit on the Kelvin scale. They're just offset by 273.15. So that's a possibility if you're going to be using it in a gas law problem. If you want to do the other way, if you're given Kelvin, you need Celsius, then you subtract 273.15. Okay. So this feels like I'm getting a little bit ahead into the working problems on Wednesday, but I'm going to introduce something called the ideal gas law equation. The ideal gas law equation. So when we say a gas is behaving ideally, I think that is so fun. Not misbehaving, but behaving. Okay, 2 things that gas is doing. Okay, so this box over here, basically these particles are not interacting at all. That's an assumption, and we do a lot of assumptions in science. It's like a basis. Okay, now things start to fall apart when our assumptions are not followed. So we assume that there are no interactions, and this is kind of a weird one. We assume that the volume of the gas particle basically is 0. It says negligible, or 0, compared to the volume of the container it's floating around in, which molecules and atoms are pretty darn small. So there are, what we're going to see though, and we don't do it in intro gen chem, but we do it in general chemistry, is that the more packed you get those particles, the denser those particles, these start to fall apart. Okay, if they're cold and high pressure, then these assumptions we make behaving ideally fall apart. So the first one is most valid, when they're not interacting with each other at high temperatures, and the other one is most valid at low pressures. Makes sense? Is that the last slide? So this is just still talking about ideal gas behavior. So we say the farther the gas gets away from being a liquid, okay, the better it will, more likely it will behave ideally. Okay. So just a glimpse at what we're going to be using on Wednesday is this here thing. You know, in physics, I kind of tell students in physics, we do a lot of like, you have an equation that relates kind of quantities, physical quantities, and then you plug them in, the quantities. That's what the ideal gas law equation is. We just plug in the pressure, the volume, the number of moles. I'll talk about what R is. It's a constant in the temperature. So, awesome. So we will pick up there on Wednesday.